Ever wondered how a jet engine works differently from a propeller engine? Today, we're diving into the fascinating world of aircraft engines and how they power everything from small planes to massive airliners. In this video, we'll break down the main types of engines, turboprops, turbofans, and piston engines, in a simple and visually engaging way. You'll learn about their unique designs, how they convert fuel into thrust, and the advantages each type offers for various aircraft and missions. Get ready to take a deep dive into the inner workings of what makes flight possible. Why aircraft engines matter. Aircraft engines are the heart of aviation, playing a crucial role in enabling everything from private flights to global travel. Without these powerful machines, the ability to transport people and goods across vast distances would be severely limited. Engines not only provide the necessary thrust for takeoff and flight, but also ensure safety, efficiency, and reliability in air travel. In this video, we'll focus on three main types of aircraft engines. Piston engines, which are commonly used in smaller planes and general aviation. Turboprops, which combine jet engine technology with propellers for efficient short-haul flights. And turbofans, the powerhouse behind most commercial airliners that offer high performance and fuel efficiency for long-distance travel. Understanding these engines is essential for appreciating how they contribute to the aviation industry and the convenience of modern air travel. Piston engines are among the oldest types of aircraft engines and are primarily used in small aircraft and general aviation. These engines have a long history, dating back to the early days of flight, and they continue to be popular due to their simplicity, reliability, and cost-effectiveness. Piston engines operate on a four-stroke cycle, which consists of four distinct processes: intake, compression, power, and exhaust intake. The process begins when the piston moves down in the cylinder, creating a vacuum that draws in a mixture of air and fuel through the open intake valve. Once the piston reaches the bottom of its stroke, the intake valve closes, and the piston moves back up, compressing the air-fuel mixture. This compression is crucial as it increases the mixture's temperature and pressure, making it more volatile. As the piston nears the top of the cylinder, a spark from the ignition system ignites the compressed mixture. The resulting explosion pushes the piston back down, converting the fuel's chemical energy into mechanical power. This downward motion turns the crankshaft, which is connected to the propeller. Finally, when the piston reaches the bottom of the cylinder again, the exhaust valve opens. The piston moves back up, pushing the spent gases out of the cylinder and completing the cycle. Piston engines are commonly used in general aviation aircraft, such as the Cessna 172 and Piper PA-28. These engines are ideal for training, recreational flying, and short-distance travel, providing a reliable and economical option for pilots. A popular example of a piston engine aircraft is the Cessna 172 Skyhawk. First introduced in 1956, the Cessna 172 has become one of the most widely flown aircraft in the world, with over 44,000 units built. Its simple design and dependable performance have made it a favorite among flight schools and private pilots alike. Fun fact, the Cessna 172 has a stall speed of just 47 knots, making it an excellent choice for novice pilots learning to fly. Overall, piston engines remain a vital part of aviation, providing power and reliability for countless flights around the globe. Turboprop engines represent a unique blend of jet engine technology and propeller systems, providing both power and efficiency for regional aircraft. These engines are designed to operate effectively at lower speeds and altitudes, making them ideal for short-haul flights and access to smaller airports. At the heart of a turboprop engine is a gas turbine that drives a propeller. The process begins when air enters the engine and is compressed by the turbine's compressor. Fuel is then injected into the combustion chamber, where it ignites, producing high-temperature gases. These gases spin the turbine, which powers the propeller through a series of gears. Unlike pure jet engines, turboprops are more fuel efficient at lower speeds, as they produce thrust primarily through the propeller. Approximately 90% of the thrust comes from the propeller, while the remaining 10% is generated by jet exhaust. This hybrid approach allows turboprops to deliver impressive performance while consuming less fuel, especially during takeoff and climb phases. Turboprop engines are commonly found in regional airliners and military transport planes. They are particularly suited for routes that connect smaller airports, where the ability to operate from shorter runways is essential. Airlines like Horizon Air and ATR utilize turboprop aircraft for their regional services, offering passengers a cost-effective and efficient travel option. One of the standout features of turboprop engines is their capability to operate on short runways and perform well in lower-speed operations. This makes them invaluable in regions with limited airport infrastructure, enhancing connectivity and accessibility. Additionally, turboprops tend to produce less noise compared to jet engines, contributing to a quieter flying experience for passengers and reducing noise pollution in surrounding communities. Turbofan engines. The powerhouses of aviation. Turbofan engines are the powerhouses behind most commercial jets and modern military aircraft. These engines combine the efficiency of a propeller with the high thrust of a turbojet, making them the preferred choice for a wide range of aircraft. Turbofans are responsible for powering some of the most iconic and successful airliners in history, from the Boeing 737 to the Airbus A320. At the heart of a turbofan engine are two main components: the fan and the turbine. The fan, which is located at the front of the engine, draws in a large volume of air and accelerates it rearward, generating most of the engine's thrust. This air bypasses the engine core and is expelled through the nozzle, providing a significant portion of the overall thrust. The turbine, on the other hand, is responsible for driving the fan and the engine's core compressor. The hot exhaust gases from the combustion process spin the turbine, which in turn rotates the fan and compressor. The compressor increases the pressure and temperature of the air entering the combustion chamber, improving the engine's efficiency. Turbofans can be classified into two main categories based on their bypass ratio: high bypass and low bypass. High bypass turbofans, such as those used in most commercial airliners, have a bypass ratio greater than 5:1. This means that for every 1 unit of air passing through the engine core, there are at least 5 units of air bypassing it. High bypass turbofans are known for their excellent fuel efficiency and low noise levels. In contrast, low bypass turbofans, commonly found in military fighter jets, have a bypass ratio of less than 1. These engines prioritize high thrust over efficiency, making them suitable for high-speed and high-altitude operations. Turbofan engines are widely used in commercial aviation, powering some of the most successful airliners in history. The Boeing 737, one of the best-selling aircraft of all time, is powered by CFM International CFM56 turbofan engines. These engines provide the 737 with impressive performance and reliability, making it a favorite among airlines and passengers alike. The Rolls-Royce Trent 1000, which powers the Boeing 787 Dreamliner, is a notable example of a modern turbofan engine. The Trent 1000 features a large, swept-back fan and a high bypass ratio, allowing the 787 to achieve impressive fuel efficiency and range. The engine's advanced design also contributes to the Dreamliner's quiet cabin, enhancing passenger comfort. Comparing engine types. When comparing aircraft engines, piston, turboprop, and turbofan, key performance metrics include efficiency, speed, and operational range. Efficiency. Piston engines are generally the most fuel efficient at lower speeds, consuming about 240 grams of fuel per kilowatt hour. Turboprops follow closely, with modern models averaging around 300 grams per kilowatt hour, making them efficient for regional flights. Turbofan engines, while powerful, typically have higher fuel consumption rates, especially at lower speeds, but excel in efficiency at cruising speeds between 500 and 1,000 kilometers. Speed. Turbofans are the fastest, capable of cruising at speeds exceeding 500 knots, making them ideal for long-haul flights. Turboprops operate effectively at lower speeds, typically around 270 to 360 knots, which suits regional travel. Piston engines are the slowest, often reaching speeds of 120 to 200 knots, making them suitable for general aviation and training. Operational range. Turbofans have the longest operational range, allowing for intercontinental flights. Turboprops are well suited for short to medium-haul routes, while piston engines are best for short flights and flight training. Best for general aviation, flight training, and small aircraft, such as the Cessna 172, where cost-effectiveness and reliability are priorities. Ideal for regional airliners and short-haul flights, like the ATR-72, as they can efficiently operate from shorter runways and at lower speeds. Perfect for commercial airliners and military aircraft that require high speed and long-range capabilities, such as the Boeing 737 and Airbus A320. The future of aircraft engines is poised for transformation, driven by emerging trends like electric engines, hybrid propulsion, and sustainable aviation fuels. Electric engines are gaining traction as researchers develop lightweight, high-power motors that could revolutionize aviation. For instance, MIT is working on a 1-megawatt electric motor designed to electrify larger aircraft, paving the way for more sustainable flight options. Hybrid propulsion systems are also on the rise, combining traditional jet fuel with electric power to optimize efficiency and reduce emissions. Companies like GE Aerospace are developing hybrid engines for single-aisle jets, aiming to cut fuel consumption by up to 5% compared to conventional flights. Sustainable aviation fuels are another critical component in the push for greener aviation, offering a way to reduce the carbon footprint of existing aircraft while new technologies are developed. With technology advancing rapidly, who knows what kind of engines will power the planes of tomorrow? The aviation industry is on the brink of a significant shift, and the engines of the future may look very different from those we know today. In this video, we explored three main types of aircraft engines. Piston engines, known for their reliability in general aviation, turboprop engines, which offer efficiency for regional flights, and turbofan engines, the powerful choice for commercial airliners. Which engine type do you find the most fascinating, and why? Share your thoughts in the comments. If you enjoyed this deep dive into aviation technology, please like, share, and subscribe for more insightful content. Thank you for watching.